Hello, ladies and gentlemen. Hope you're all doing well. Today we are going to be talking about Transformers. Not actually these kind of Transformers, I'm sorry. However, if you would like, feel free to go and watch the Transformers movies. They are awesome, even though it doesn't relate to physics. So, what we're going to be doing today, we're going to go through, I'll talk through these slides, give you an example for Transformers. And then you're going to complete day 13 exit ticket in Google. Just so you know, the day 13 exit ticket, that one actually has to do more with just EMF, which is okay because Transformers use EMF anyway. But just so that you are aware, you won't see any direct Transformer problems on that exit ticket or on that assignment. Okay. So you'll do the day 13 assignment, and then you are going to be having your test tomorrow. Okay, so please make sure that you are aware of that. And the test is going to be all multiple choice. At this time, I'm not 100% certain on how many multiple choice questions there are going to be, so I'm not going to say for sure right now. So let's just kind of review electromotive force. Remember, that's when we have moving a magnet next to wires to induce a current, or you could do the opposite. You can move the wires next to the magnet, either one, as long as they're moving next to each other to induce a current. And we can change the number of loops, change the cross-sectional area, change the magnetic field, or when we're moving it, we can move it faster or slower. And we use that equation, electromotive force is equal to a change in turns on wire area multiplied by my magnetic field, and then dividing that by time. And remember, time basically represented how fast you are moving it next to the coil of wires. So transformers is what we're talking about today. And transformers, what they do is they increase or decrease that potential difference or the voltage. When they do this, they waste very little energy or power. We're going to say, for our purposes, we're just going to say that there is no energy lost. In the real world, there would be a little bit, but we are just going to treat it as a transfer of 100% power. I should be saying power, not energy, because all energy is conserved, and we should know that law of conservation of energy. Okay, so we can have current traveling through a wire, and we know that creates a magnetic field, and we know that changing magnetic field creates current in the wire, and transformers actually use both of these. So I'll have you watch a video here in a little bit, but just briefly, a description of what a transformer does is essentially it sends current into a wire, and then that wire gets wrapped around a coil in an iron core, creating a magnet and a magnetic field. And then from there, that magnetic field induces current into a next set of coils in a wire, right? And there's a really good video that I have here that shows exactly what that is. So there is this video here that is linked onto your Google Slides. If you could go ahead and watch that, that would be awesome. And then you can resume this video. So hopefully that was a pretty informative video. I really like it. I think it does a great job of explaining exactly how transformers work. So we had, I don't know if they use this terminology. I don't recall if they use this terminology in that video. But you saw on each side of the transformer. So if this is my transformer, I had coils on this side, and then I had coils on this side. I guess I'll make this one have more coils. So this will be a step-up transformer. We have what we call primary and secondary coil. So I would consider the one on the right to be my secondary coil, and the one on my left to be my primary coil. And just for the sake of keeping everything the same, we'll always work from left to right, just like reading a book. So we'll always have our primary on the left and our secondary on the right. So initially, we have current running through this. We have current running through. Sorry, messing with my mouse here. I have current running through this coil over here, the primary coil on the left side, and that is going to induce a current, or sorry, that's going to create a magnetic field in this iron core, and that magnetic field is then going to induce current into this wire over here. So we're going to get current induced into that wire, and then that's going to continue moving down the circuit. Okay. Dun, dun, dun. So taking a look at how this relates to power, which is something that you will have to know how to calculate, and it's really not too difficult. We're changing the number of loops, but we are going to say that we have constant power. And if you recall, we said power was equal to current times my voltage. We have two kinds of transformers. We have what we call a step-up transformer, which, if you remember from that video, it talked a lot about step down transformers when it goes into our house, but step-up transformers actually used right after it goes right after the power is created at the power plant. They step up the voltage, and then before it gets to your house, they step down the voltage. So with a step-up transformer, in that primary loop, or in that primary coil, let me make my transformer over here again. So on the primary side, we're going to have less loops. And then on the secondary side, we're going to have a lot more loops. Okay. And we are going to be increasing that potential difference, or increasing voltage. All right. So voltage is going up. And then the current going from primary to secondary, that current is going to be decreasing. Okay. And then for step down, everything's just going to be the exact opposite. So with a step down transformer, we're going to have where we have a decrease in loops. So in my primary, I'm going to have a lot of loops. And then in my secondary, I'm going to have very few loops. Exact opposite for voltage and for current as well. So now as we go from left to right, we have a decrease in voltage. So that's the whole point. That's what we call it, a step down transformer. We're stepping down the voltage. And as we go from left to right, we're also increasing my current. Okay. Oh, I didn't want to do that, but that's okay. Okay, so here's just kind of I guess these pictures are probably a little bit better than my pictures that I had there. So taking a look at these pictures, you can see how over here you have on the left side for the step-up transformer, you have less coils going into more coils, or they're calling them turns in this case. But the power is staying the exact same here, as you can see, because if we take 10 times 10, or 10 times 100, we get 1,000 watts. 400 times 2.5, we get 1,000 watts as well. So we're going to treat the power as staying constant, even though our voltage is increasing and our current is decreasing. So what this tells us, what we can do, since we know that power is going to be staying constant throughout every one of our transformers. Oh, sorry, I guess getting a little ahead of myself here. It just kind of shows you a picture of going from power station to step-up transformer onto the power lines, and then before it gets to your house, it goes into step-down transformers, and it doesn't, along the way, it usually goes into multiple step-down transformers. It's not just one massive one next to your house. So, as I was saying before, since we know that we're going to be keeping power 100% efficient, we can set up a couple ratios here. I'm going to say P sub P is equal to P sub S. And what that means is that's going to be my primary power is going to be equal to my secondary power. All right, well, if we know our equation for power is current times voltage, then we can say that current in my primary times voltage in my primary is equal to current in my secondary times voltage in my secondary. And what this allows us to do, it allows us to set up some ratios that come in pretty handy. So if you rearrange this equation so that you have your currents set up as a ratio and your voltages set up as a ratio, you end up with current in the secondary over current in the primary is equal to voltage in the primary over voltage in the secondary. And we can add one more in here, and that is dealing with the number of turns. We know that the more turns that you have, the more induced voltage you are going to have. So therefore, what we can also say is that as we increase your voltage, so the ratio is going to be equal to the primary voltage. So over here, we would also have voltage in the primary over voltage in the secondary is equal to the number of turns in the primary over number of turns in the secondary. So you can take any one of these three ratios here and set them equal to one another. So I can set current equal to turns, I can set voltage equal to turns, or I can set current equal to the voltage ratio. Any one of those would work. So moving on to an example problem here. If I have a step-down transformer, it's using 5,000 primary coils and 300 secondary coils to reduce the EMF in the secondary coil to 120 volts. What is the voltage entering the primary coil? All right, well, think about what we're dealing with here. We're using coils. I have coils in the primary and secondary, and then I have EMF or voltage in the secondary. And I want to know voltage entering the primary. So the ratio I'm going to be using is that number of turns in the primary over number of turns in the secondary equal to voltage in the primary over voltage in the secondary. And now I can set up my ratio. So I would have 5,000 turns dropping down to 300 turns is equal to my voltage in the primary, because that's what we do not know, divided by my voltage in the secondary, which is 120 volts. And now I can solve for this ratio. Take a second to solve for that. And hopefully you end up getting 2,000 volts in that primary. Okay. Next it asks us if it takes 1.5 amps through the secondary coil to operate a toaster, how many amps are running through the primary wire? Now we are going to be under the assumption that we are still dealing with this problem. I guess I should have said that, but under the assumption that we're still using this 2,000 volts as we're talking about this transformer here, going from 2,000 down to 120 volts. So we would say, sorry, let me get a little bit ahead of myself again here. So what we're going to use is we are going to say that we have my voltage in the primary over voltage in the secondary. That is going to be equal to my current ratio. Now remember, these are inversely related to each other, so I'm going to have current in my secondary over current in my primary. So now I set that up, plug in. Now I'm just going to plug and chug, so I plug in all my numbers. I have that 2000 volts that we solved for before over 120 is equal to, in my secondary coil, I have 1.5 amps. So that'll go on top here, divided by the current in my primary. Okay, now I'll go through this just to kind of make sure that everyone knows how we actually go about solving for one of these, just in case it's been a while since we cross multiplied. So make sure that when you go to cross multiply, what we would do for one of these problems is I cross multiply each of these. So when I take 1.5 multiplied by 120, I get 180 is equal to 2000 multiplied by current in the primary. So I get 2000 current in the primary. And then I can divide over to solve for current in the primary, which should end up being 0.09 amps. All right. So hopefully that's not too difficult. If you have any questions on that, please make sure you let me know. We don't directly have an assignment relating to these transformer problems. So if you have any questions on this, please make sure you let me know. But then your assignment, make sure that you are completing the day 13 exit ticket. Should be a couple problems from this day 13 assignment. So make sure you're completing that. As always, you're not submitting the assignment. Just make sure you plug your answers into a Google form on the exit ticket. And then do not forget, your test will be tomorrow. Hope you all have a great day.